Welcome back to Probability and Statistics. In this video, I'd like to show you how to use Desmos's uniform random number generator to simulate other kinds of random variables that aren't necessarily uniformly distributed. In particular, in this video, we're going to look at using the generator to simulate exponentially distributed random variables. So let's take a look. What we want to do in this example is simulate an exponential random variable with parameter lambda equal 1/2. So to use Desmos to do this, we're first going to create a random number generator that models the uniform distribution on 0, 1. That's the first step in every application of the inverse CDF method. Then we'll generate 10,000 simulated observations from the uniform distribution on 0, 1. Then we'll apply transformations to create 10,000 observations of our exponential random variable with parameter lambda equal 1/2. And then we'll finally make a histogram of those observations and compare it to the density curve to see that, at least visually, we get a good sense that the observations indeed are following the exponential distribution with parameter lambda equal 1/2. So let's see how it's done. I'm going to open up a Desmos graph. So just go to desmos.com, go to the graphing calculator. And the first thing we need to do is create a uniform distribution. I'm going to go ahead and comment things so I can reconstruct what I'm doing. We're building our pseudo-random number generator on the interval from 0 to 1. Creates uniformly distributed values between 0 and 1. So that's D equal, you just say uniform dist, and then 0, 1. This says, give me a uniform distribution on the interval from 0 to 1. There you see the density function being plotted. We really don't need that right now. Next, what I want to do is generate 10,000 observations from that. So I'll make a note to myself. And all we need to do here is ask the generator D to do that. So let me call these observations, let me call them U since they're uniform. You can use a different variable name. You'd say D dot random. That's saying generate random samples from the distribution D. And then you tell it how many random samples you need. We want 10,000. And the next thing we want to do is apply some transformations to those observations with the goal of ultimately coming up with exponential observations with parameter lambda equal 1/2. We need to remind ourselves of some of our theory here, but we have all the tools we need to do this. So here's the relevant facts. The first comes from example 2.22. It says that if y has the uniform distribution on the interval from 0 to 1, then x equal negative natural log of 1 minus y has the exponential distribution with parameter lambda equal 1. So that's how we could generate exponential observations from uniform observations. But we really wanted observations from the exponential distribution with lambda equal 1/2, right? So that brings in another fact from our work this semester, and that is that, actually it's a homework problem. If x has the exponential distribution with lambda equal 1, and mu is a positive real number, then mu times x has the exponential distribution with parameter lambda equals 1 over mu. So those two facts together can work together to give us what we want. Let me show you how it's done in Desmos. The first thing we want to do is apply a transformation to get the exponential lambda equal 1 observation. So let's apply the transformation y equals minus natural log of 1 minus u to generate exponential observations with lambda equal a half. So all we need to do there is say y equals minus natural log of 1 minus u. U are uniform observations, right? So there we have it. And those should be, according to example 2.2.2, exponentially distributed with parameter lambda equal 1. I need to multiply now those to get a different lambda, right? If I want lambda equal a half, using homework 5, question 1, I need to take my exponential distribution with lambda equal 1 and multiply it by 2. And that'll give me an exponential distribution with lambda equal a half. So let's do that here. Give myself a note so I can document. And then I'm going to apply the transformation x equals 2 times y to generate exponential distribution with lambda equal 1/2. And I can see right now that my note up here was incorrect. That should have been 1. Okay, and so let's do it. X equals 2 times y. There we have it. And now let's make a histogram and see whether these values appear to be following the exponential distribution that we want. So let's create a histogram of the x values. So you just type histogram x and then give it a bin width. I'm going to start out with a bin width of 1/4. Again, we'll always want, in these kind of problems, the bar heights to be scaled with the density option. That just makes the total area under the histogram 1. And we want the bin alignment to be left, not center. And then we'd probably want to kind of squeeze in on this we're on a different viewing window. It looks like my x values are going, wow, it looks like I've got, well, I could actually find out here. The maximum of the x values is actually 23.56. So I better set my viewing window to something like this. Go over to the graph settings here. My x-axis needs to go from like minus 0.1 up to like 27, right? And then my y-axis looks like needs to go from minus 0.1 like maybe, yeah, actually I could probably get away with something like 0.5, right? So there we see our histogram. And let's see how well it follows the density curve we would expect. So let's compare the histogram to the density curve for the exponential with lambda equal 1/2 distribution. That density curve, as you well know, is y equal 1/2 e raised to the minus 1/2 x power. Let me make that curve red. And there you see it. It does look like the histogram is very closely following that density curve that it should, right? The distribution that we're aiming for here. Let me just point out a couple of things too here. You can use the randomize button here to create a different set of 10,000 samples in step 4 here. And then that'll ripple through automatically to all these other steps. And if I do that, I would expect this histogram to change slightly in terms of the fine details, but it still ought to follow my red curve, right? And so let's click the randomize button. Bang, there it goes. Still following the exponential lambda equal 1/2 density curve that we would expect, and that'll continue to be the case if you get more randomizations. Those histograms are all following closely the theoretical density curve, which is what we want to happen, right? Finally, you might want to save your graph. You need to be logged into Desmos to do this, but all you do there is say save and give it a name. So we could say, if this were a homework problem, you might just say homework 5 problem, whatever it is. Maybe this was problem 3. You can say save. And then to share that graph, and I'll ask you to share some of your graphs with me, go over here to the share icon right next to your name. Again, you'll need to be logged in, so you'll see your login name here in the upper right. And this icon right next to it is the share icon. Click on it. What you want to do is copy this web address right there. Copy that web address. And then in a homework problem, you could simply paste that web address as into the solution area for the homework problem. So that in a nutshell is how to use Desmos's uniform random generator to generate actually observations from a different distribution, in this case the exponential distribution. The key ideas here, we're using the inverse CDF method to do this. Example 2.2.2 was that inverse CDF method applied to the exponential distribution. And in your homework, I'll be asking you to do further problems of this sort for other kinds of distributions. So I hope this has been helpful. If you have questions, let me know, and we'll see you back here again real soon.